In the second video for the Part C lecture notebook in Module 3, we go over rather briefly an introduction to widgets. Widgets are something that we use far more extensively in Module 4 when we're discussing computational applications, but we introduce them here so that you become somewhat familiar with their use. Now, widgets are great for adding interactivity with functions. They're very useful for illustrating concepts and exploring ideas, and they are very useful when we are visualizing the impact of results in plots. To read more about how we can use the interact widget, check out the documentation that's linked to here. And there's also other documentation you can read. I'll just go ahead and click on it. You can see that it describes using interact, how to the basic interact function, as well as fixing arguments using fixed. And you can see that in the code here from IPy-widgets, so it's interactive Python widgets, I am importing the interact, the interactive, fixed, and interact manual. Now, I normally actually don't use interactive, but I use interact, fixed, and interact manual all the time. But I generally just copy and paste this anywhere when I want to use widgets. And then I also import the IPy-widgets as widgets, which is useful for accessing the various other things that I don't want to type in widgets dot. Like I usually just like to say interact, fixed, interact manual instead of saying widgets dot fixed, widgets dot interact. But for everything else, I do widgets dot and then whatever it is instead of importing all the individual things as they are and remembering the names, because then I can use the autocomplete. But I use interact, fixed, and interact manual so much that I just import those names directly from IPy-widgets, those methods, and then everything else is within IPy-widgets as widgets imported there as that nickname. So it's really cool. You can play around a lot with it. I really recommend you try to explore and do your own things based on the documentation about interacting here. So check it out, play around with it. It's pretty fun. So I'm just going to go ahead and run this here just to import this in the Colab environment. And now I'm going to show you our first interactivity. So I'm going to use the interact function from the IPy-widgets, and I'm going to use it on the myFun function. So this was the function at the very top of this notebook where I was plotting this interesting like e to the negative x squared sine of pi x that I just used to produce some interesting plots involving the function and its derivative approximations. But here's a function that's just f of x. And you might want to know, hey, I would like to see what that function evaluated at different x values are, and I don't want to type into code myFun of and then all these different x values and then rerun code over and over and over again to see what the outputs are. So what you can do instead is you can say interact with that function, and then for the particular input you have a comma, and then for any other parameters that are here, this only has one x, it has an x parameter. Then you can assign that its own widget, and I'll make it a slider of floats. I'll assign it an initial value, a min and max value, and the step size. As I move the values along with the slider, it will step in increments of 0.1. And then what I'll be seeing are the outputs of this function on the screen, because this function, if we go back to it, so I'll just zoom out. Oops, I switched the code there. Okay, so I zoomed out. If we look back at this function, myFun, you'll see what I'm returning is the output of the evaluation of that function at a given x value, or an x array. In this case, I'm just feeding it an x value. So because that's returned, that's producing a standard output, so it's then printed to the screen, even though I'm not using a print command because there's nothing else that's happening in this code cell. So let me just go ahead and run this. You can see here's the x value for the slider. At 0, the output right here is a value of 0, right? So it's also showing what's going on here. That function, which is the myFun, and it's within, this is just basically saying it's within the main namespace of my notebook here. But my function is being evaluated at x equals 0, and the output of it is 0. And now this slider, I can click on it. If I've selected it like this, I select it just like that. I've clicked on it with my keypad on my laptop. I can now use the arrow keys, the left and the right arrow key, to move it around. You see it moves in increments of 0.1. And then I see the output value printed here. It's at 0.305. Now you'll notice this did not change because this is just printing whatever the initial output value was, or excuse me, what the initial input was based on that value. And if I keep moving this around, 0.2, 0.3, incrementing in steps of 0.2, you see how the output's changing of the function. So I'm just immediately getting a sense of the function. I can also drag the slider around, and then I'm just immediately seeing what the output evaluations are for that function. So that's kind of it. That's like how I can immediately start exploring a function and how it responds to varying inputs very quickly. And if the function was a function of, let's say, x and y and z and all sorts of different variables, you would just have to have different things for each one. I could have y equals and then something like some sort of widget for it, or I could fix a value. That's where the fixed comes in. If I want it to be fixed, I might say y equals fixed 3. Now this is going to produce an error. Or actually, I guess it didn't do anything. I guess it must just be ignoring it. I thought it would have produced an error because the function doesn't depend on y. So I guess if you put in extra things and the function doesn't depend on it, they're just ignored. I would have assumed it would have produced an error, but this function doesn't depend on x, y, and z. It just depends on x. But I was just trying to show you would separate the parameters with a comma. Now you can also do it all in one line, but I like to generally have the function, the object I'm interacting with on one line, comma, the parameters, comma, like on each line, each parameter, each input to that function, and then on the whenever you get to the last one, you just don't need a comma at the end of that, and you just run it again, and you get that output. Now let's look at interact manual. What do you think the difference is going to be between interact and interact manual? Now again, look, as I drag the slider, you can see that the outputs are immediately displayed. Let's go ahead and run this. Everything else is the same. I have my function, I have my input as this float slider, and when I run this, you see there's this run interact button. You don't see any output right now. And if I move the slider around, you also don't see any output. Once I click run interact, you see the output printed beneath it. And if I move the slider again, no change in output. I have to run interact again. That's actually really useful if you want to be changing values and the output that what's happening with the function takes a second. It might take up just a bit for it to display correctly. And if you're just randomly changing values, like you want to move things around quite a bit and there's a few inputs, you might not want to see all those things created, especially if the output of your function is a plot and the plot has to get refreshed as it's sliding through all the values. I often use interact manual so that I can control, like, now that I have the inputs what I want, run interact. Now that I have something else, run interact again. So it just gives you that control of maybe oh, it wasn't 0.7, I don't want that, I want it to be 1.0. Now I'll run interact and I just immediately get that output. And again, what's nice is I don't have to run the function. Like what I'm avoiding doing here is saying, let me just click somewhere else. Oh, by the way, you can also click on these values and just put something in here like 0.9, let's say, and I can get what, now, and again, I have to run interact to get the output, but you can set the values instead of using the slider if you want by just selecting on the value. But let's go ahead and say that I created another code cell right here. What I'm avoiding doing is having to do this. Okay, what is it at 0.9? Oh, that's what the value is. What is it at 1.0? I'm coming back up here and okay, 1.0, and rerunning the code cell. Like I'm avoiding having to constantly change the inputs and then running a code cell in order to see what the output is. I'm just going to zoom out and delete this. I'm able to just move a slider, and when I just run interact and I see the output. It's a simpler way for me to interact with the function. It's more convenient. The other thing you can do, which is really useful, is you can create the slider as its own separate object. So I can say, well, the x values I'm interested in are based on this float slider, this slider of float values, and I can then do that, say x vals equals this widget float slider, and then my interact function becomes much simpler. Like it's just my fun and x equals x vals. And again, you could write that like this. I often like to do it like that with then the parentheses are kind of lined up, so I can just see my inputs. When it's short enough, though, I don't really bother. But when I'm putting the widgets inside of the interact or interact manual function, then I will often separate them in their own lines. But if I was going to make all the input sliders or fixed values their own objects, I would probably then, unless there was a lot of inputs, write it all in a single line of code. That's just a preference. But I'll just show you if I run this here, again, you see this is the interact, so not interact manual. So as I move this around, you can just see the values updating kind of pseudo immediately, almost immediately, as I move that slider. You can also restrict inputs to be integers. It's pretty obvious. Instead of a float slider, you make an int slider. Here I'll set the value to be 1. I'll make the min -5, max 10 in 1. You could make step 2, you can make step 3, 4, whatever you wanted, but I'll just do it like that. These are my int vals, and I'll make x equal to my x int vals there. If I run that, again, you'll see x goes 2, 3, 4, 5, 6, 7, just jumping in terms of integers. Look what happens if you try to make this, let's say, 1.5. So that's 1, and then if I move it, you see, oh, it's 2, it's 3, it's 4, because it's an int slider. So that step 1.5 doesn't work. You should choose your step size to be an integer. But I can make my step size be 2. So if I start at 1, now look, it's 3, it's 5, it's 7. Can I make it 4? Yes, I can. If it's 4, look, it just jumps up to 7 again because it's doing the increments based on that initial value of 1. So but I could see what it is at 0 if I plug in 0 there. I can just select that and input it because that is an integer that's going to be a valid input into this slider. I wonder if I can actually make it a non-integer by inputting it. No, I can't. The int slider is forcing it to be an integer for an input. So I think it's just casting it as an integer. In some cases, we want to have values range over orders of magnitude. When that's the case, we want to use a float log slider. The keyword value is just the value. So here what I'm doing with this float log slider is I'm saying start at 0.73. I'm just showing that this just can start at 0.73. I've already run it. You see it starts at 0.73. But then I'm saying start at a base of 10 and then go through values that go from 10 to the negative 5th power up to 10 to the 1st power, and do it in steps of 0.5, which is the exponent step. And you can read more about this. This is this first link here. If you go to this, or excuse me, the second link for the widgets, this widget list, you can read about the float log slider here and how it works. So I just found it for you so you could identify it. There's also these various different types of sliders. There's so many types of inputs, these different types of widgets that you can find that you could spend some time going through here, figuring out how you want to do it. You could do like drop down type menus, radio buttons. There's all some really cool stuff that you can play around with. A lot of it I don't use. Checkboxes are nice if you have different types of options that you might want to have, as like plot with this feature on or off, like in a plotting function that you have a widget with, where you might want to include the axes or not include the axes, like some sort of plot of representative x and y axes on the figure. Things like that, where you might have some if-else condition with a keyword where you just say, hey, if it's true, plot these things, if it's false, not, and then it's a checkbox for that. So you can play around with this a little bit, is my point. There's lots of options. But as far as the float log slider goes, it's pretty straightforward. You run it and you'll see like it starts at 0.73. But then if I start moving the slider around, you see, oh, it's 3.16, and then it's 10. That's 10 to the 1st power. But between 10 and 1, which is just 10 to the 0 power, it goes to 3.16. What's with that 3.16 value? Again, it's the step size. So if you look at this scratch cell here, 10 to the, let me just do 0.5, which is the square root of 10, is 3.16. So you see the 3.16 value. This is the step. When it's 10 to the 1st, we're at 10. That's that output here. Of course, that's the value of the input. The function is still being evaluated there, and this is what the output's being printed to the screen here. But then when I slide this just 1 over, it's 3.16. Well, that's taking a step size of 0.5 in the power. And then 10 to the 0, we know, is 1. So there you go, 10 to the 0 is 1. 10 to the negative 0.5, if I run that, you see that's 0.316. And of course, as I continue to slide x down, so there's 1.316, right? Again, 0.316, 10 to the negative 0.5. So that just gives you kind of a sense of what's going on with these inputs related to using a float log slider. If you would like to just jump over whole orders of magnitude, you make your step size 1. If you want to jump over half, excuse me, orders of magnitude, do a step size 0.5. You can make this 0.15 if you want. You could do kind of whatever you want with this. I generally like to do it in orders of like half a order of magnitude, but that half order of magnitude is kind of a little weird. It doesn't go like 1, 5, 10. It's going to go 1, 3.16 and then 10 because of 10 raised to the half power. So that's why I just made this part of the video its own separate thing, is I think it's worth isolating that because the float log slider can cause some confusion. So it's worth just thinking about and experimenting with a bit on your own. So that's it for kind of the main lecture part of this notebook. And the last part of this video will go over the solutions to activity 2. This activity is actually rather straightforward. What we're doing is something a bit more fancy than the types of function interactions we were seeing above, where we're just returning the value of e to the negative x squared sine of pi x. I think that's what it was, evaluated at some x value. So it was pretty straightforward what that function was doing. And it was pretty easy to just give it inputs that we vary, and then we see what the outputs are. But here what we're doing is we're actually creating a plot function. And in that plot function, we're having some granular control. We feed it a function f, and then h and n that describe how we should be estimating and plotting a function in its derivative approximations. So this is going to be a little bit interesting. This is definitely a place where you want to use that interact manual function, because otherwise you can get some weird flickering and weird stuff that's going on as you're moving sliders around and the plot's trying to continuously update until you get to the values you want. So what you have to do, the part that you have to do, is add comments to every line of code. So when I'm grading this, I'm literally going to go through and I'm just going to check that you added a comment to every line of code to just make it clear that you understand what every single one of these lines of code is doing. A lot of this is stuff that was discussed earlier in the first video for this lecture notebook. But it's pretty straightforward. Just add really short comments like this is creating a figure, right? This is creating a lin space of points from 0.05 to 1, and it's creating n of them. So it's creating n points from 0.05 to 1. Like that would be a way to have that code comment. And this would be the forward difference approximation of the derivative, backward difference, center difference approximations. Creating an axis, plotting the original function, adding a title to the function plot, creating another set of axes, and then plotting the different derivative approximations, the forward difference, the backward difference, and the center difference. So some of these, you can make your inline comments rather short if you add maybe a comment here like below we plot the various finite difference approximations to the derivative. So maybe just say to the deriv, and here you could say forward diff, backward diff, and so on. Like you could, by having some comments be a little bit more detailed, like that are above a line of code, it allows you to perhaps simplify the inline comments that follow. So that's just an idea, like how you might structure it, something to think about, just good commenting. But I want you to go through, add comments that what all of these lines of code do in this particular code cell, as well as this code cell. Here's just a new function, by the way. It's x squared times sine of pi divided by x. That's what's going on here with that function. And now here, I'm doing this. You could say, what's going on here when I do that reset force out? That's clearing the memory. It's basically saying like remove the output from memory that's associated with this cell every time I run it. So it's just like when you're creating plots and doing interactive widgets with plots, it's often very much the case that you're regenerating them. You might rerun these over and over again as you play with things, but also as you regenerate just a plot over and over again in a code cell, whether it's a widget or not, it creates new figures and it takes up space in memory, and you can actually kind of get a bloated amount of resources taken up by your Jupyter notebook. And this just kind of helps manage the resources a little bit better. You don't have to do it. Everything will run fine, but I mean, I suppose you could probably push it to the limits. And this, I think I've seen it to be less of an issue in Colab, but when you're running a Jupyter notebook on your own computer, this really helps save the resources because you have far generally fewer resources on your local computer than what Google's giving us for free on Colab. So now here's my interact manual with that plot derivs function, and then I'm using that fixed function to fix the function, my f, and then I'm letting h vary over orders of magnitude using that float log slider, and then I'm letting n be an int slider. So n is representing a number of points, so that has to be an integer. If I try to make this not an integer, that's a problem in the lin space. It's expecting a variable of type integer here for that last one to find the number of points. So let me just go ahead and run this. So you should be doing the code, and you also need to interpret the result in the markdown cell. So I'm going to explain a little bit about what's going on. You need to put this in your own words in this markdown cell, this text cell below. But look what happens with h being 0.01 and n is 10. Now, h is varying by an order of magnitude, and I'm letting it go basically from, so it's base 10, I'm letting it go from 10 to the negative 2 as the max. So that's 0.01 is where it's starting, down to 10 to the negative 16th. And you might remember from video 1 that we do encounter quite a bit of approximation error with the derivative as soon as we make h small enough. And 10 to the negative 16th is definitely going to be small enough. Now, n is controlling the resolution of the plot. I'm using initially 100 points, and then in step size of 50, I can go down to 50, that's the minimum, or I can go up to 1,000 points. Now, when I run this, so I've already actually run that, let me run interact, 100 points. Here's this approximation, this function, here's this plot with what was it again? I forgot already. X squared times sine of pi over x. That's what's being plotted here. And this is what the derivative approximations look like to this function. And you can say, oh, okay, there's something weird's kind of going on here. It's looking kind of sharp. Maybe you want to increase the n. And you can kind of go up to, like, let's say 400. And you see what happens is these oscillations, they're happening faster as you go towards 0, but the magnitude is shrinking down. So that's apparent from the function. As x is going towards 0, then 1 over x is going towards infinity as I decrease towards 0. So sine of pi x is just oscillating through, like, all the oscillations that sine of x does on the real line. I'm just kind of forcing all those oscillations to happen more and more quickly as I approach 0. Now, of course, that's why I have my linspace go to 0.05 instead of at 0, because I have a problem. I don't want to divide by 0 in this function, get not a number. Even though it doesn't get an error, I just don't want to deal with the issue or a warning. But I'm multiplying, right? Sine is always taking this input, and even though it might be oscillating faster and faster because 1 over x is basically going to infinity as x goes to 0, but sine is always between -1 and 1. And then when I multiply it by x squared, which goes to 0, it shrinks the size of the oscillation. So even though they're happening, the oscillations are occurring faster and faster and faster, I'm shrinking the magnitude of these. And if you look at this, you go, okay, I can increase the resolution to make the plot look a little better. It looks smoother than what it was when it was, like, I mean, go down to 15. It looks a little jagged. You can see there's a resolution issue, and that the plots of these don't look great because I just don't have enough points to resolve the variation in the functions. If I make n super large, like 1,000, then my plot is about as smooth as I'm going to make it, at least in the range of n values I gave. And you can look at this and say, well, that's maybe the approximation of the derivative. But that's when h is 0.01. If I step down an order of magnitude to 0.001 and I run interact, look at the difference. So h is controlling the accuracy of my derivative approximation. N is controlling the resolution of my plot. So these are different things, and they're going to give you they're going to control different aspects of how these plots appear. If I shrink h down more and more and more, let's go to like 1e-7, right? So there's my derivative approximation, right? And it's looking okay. There's a little bit of a resolution issue there. I can, of course, make this look better. If you look at that, these heights look a little off. That's because the n is 1,000. I can make n equal, like, 20,000, 100,000. At some point, though, it's just ridiculous, and you cut it off, and the plot's just as good as it's going to get. But imagine that I make h even smaller. I'll just go all the way down to the bottom, 10 to the -16. Now I plot it. Here's those derivative approximations, right? This is where they're really kind of like all garbage. They're following the trend of the function, but the values are way off. There's all sorts of error. It's very jagged, and this is, again, encountering that finite precision arithmetic issue, round-off error, all the things that are polluting our ability to compute with really small numbers, and like when we're getting things that are getting close towards 0 divided by 0 in this case. But there's lots of issues with approximations and various inputs, and you don't necessarily know where they're going to occur. Here I know it's going to be when h is getting close to 0. That's going to impact the approximation everywhere. But I'm going to have pretty good values, maybe down to like 10 to the -9 happens in this case, although it already looks a little jagged there to my eye. So anyways, you need to explain what's going on with the h and n kind of in your own words, the way I just, along the lines conceptually of what I just described in this. I think it's just a good practice for you to try to explain this in your own words, use some bullet points, and some ideas of values you played around with and what makes certain concepts more apparent with certain choices of n and h. That's a good exercise for you to do. That's a good way for you to finish this activity, along with also adding the code comments. And that's all you need to do. And then, of course, you have your summary activity to do. Thanks for listening.